Deep beneath the layers of rock that record Earth's history lies a question so unsettling that most scientists avoided asking it for decades. What if we're not the first? What if, millions of years before humans evolved, another intelligent species rose to industrial civilization, built cities, harnessed energy, transformed their environment, and then vanished? Would we be able to detect their existence today? Or would deep time have erased every trace, leaving us to believe we're the first technological species this planet has produced? The answer is far more disturbing than you might think, because the evidence suggests that an industrial civilization could have existed on Earth and left almost no detectable trace if enough time has passed. This isn't science fiction. It's a serious scientific hypothesis that forces us to confront how little we actually know about our planet's deep history. Hit that like button and subscribe as we explore the most unsettling possibility in paleontology. Prepare yourselves. We begin. The question gained scientific legitimacy in 2018 when astrophysicist Adam Frank and climate scientist Gavin Schmidt published a paper in the International Journal of Astrobiology titled The Silurian Hypothesis. The name references a Doctor Who episode where intelligent reptiles evolved on Earth before humans. But the science is deadly serious. Frank and Schmidt weren't claiming that ancient civilizations existed. They were asking a more fundamental question. If one had existed, what traces would it leave in the geological record, and could we detect them today? Their conclusion was sobering. An industrial civilization that existed more than a few million years ago would be extraordinarily difficult to detect. Most of the evidence we think of as permanent, cities, roads, buildings, even plastics and metals, would be completely destroyed by geological processes long before 10 million years had passed. The Earth is a recycling machine that systematically erases evidence of surface features through erosion, plate tectonics, and metamorphism. Given enough time, almost anything can be ground to dust and subducted into the mantle. To understand why this matters, we need to grasp the timescales involved. Humans have been anatomically modern for about 300,000 years. We've had agriculture for roughly 12,000 years. Industrial civilization, the kind that significantly alters the environment and leaves widespread physical traces, has existed for only about 250 years. This is a geological eye blink, so brief that it barely registers on the timescales geologists work with. Now consider that complex multicellular life has existed on Earth for over 600 million years. The Cambrian explosion, when diverse animal forms first appeared in the fossil record, happened about 540 million years ago. For perspective, if Earth's history were compressed into a single year, humans would have appeared in the last few hours of December 31st. Industrial civilization would have existed for less than 1 second. There are 540 million years of history before us, during which complex life existed. That's over 2 million times longer than industrial civilization has existed. The question becomes stark. Could an industrial civilization have existed during that vast expanse of time and left no trace we've yet discovered? Before you dismiss this as impossible, consider what we actually know about the fossil record. Paleontologists estimate we've discovered perhaps 0.1% of all species that ever lived. The fossil record is extraordinarily incomplete, biased toward organisms with hard parts like shells and bones, toward marine environments where fossilization is more likely, and toward more recent time periods where rocks haven't been as thoroughly recycled. We have identified roughly 300,000 fossil species in the scientific literature. Estimates suggest that over 4 billion species have existed throughout Earth's history. We found evidence of less than 1/100th of 1% of all species. The vast majority of life that ever existed left no trace we've discovered. Most species probably left no trace at all, their soft bodies decaying completely without fossilizing. If the fossil record is this incomplete for organisms that existed in large numbers across wide geographic areas for millions of years, how complete would it be for a hypothetical intelligent species that might have had a small population concentrated in specific regions and existed for a geologically brief period? The answer is troubling. We might never find their fossils at all. But surely an industrial civilization would leave more than just fossils. Cities, infrastructure, technology, all of this would leave traces, right? This is where the timescales become crucial. Over millions of years, geological processes are relentlessly effective at destroying surface features. Consider what happens to a modern city if humans suddenly disappeared. Within decades, buildings begin to collapse as steel corrodes and concrete cracks. Within centuries, most structures have fallen. Within thousands of years, erosion has reduced everything to rubble. Within tens of thousands of years, glaciation or river meandering or coastal processes could completely bury or remove that rubble. Within millions of years, plate tectonics could subduct the entire region into the mantle or uplift and erode away all traces. The only human structures likely to survive millions of years are things we've buried deep underground, like mine shafts and deep foundations, and even these would be destroyed if the region underwent significant tectonic activity or erosion. Everything on the surface, all our cities and infrastructure, would be ground to dust and scattered long before 10 million years passed. What about materials? Surely, plastics and refined metals would leave chemical traces even if physical structures don't survive. This is partially true, but the timescales still work against detection. Plastics degrade over thousands of years, breaking into microplastics and eventually into their constituent molecules. In an oxygenated environment, most organic compounds oxidize and break down. Even if plastic molecules persist, they'd be scattered through sediments at such low concentrations that detecting them millions of years later would be extraordinarily difficult. Refined metals are more durable, but face their own challenges. Iron rusts, aluminum oxidizes, copper forms compounds. Over geological timescales, refined metals disperse and chemically alter until they're indistinguishable from natural metal deposits. We might find a localized concentration of certain metals in a sediment layer, but how would we know it was artificial rather than a natural ore deposit? Gold and platinum group metals are more resistant to chemical alteration, but unless an ancient civilization used them in massive quantities and concentrated them in specific locations, detecting them millions of years later would be nearly impossible. We'd need to find a sediment layer enriched in these metals at levels far above natural background, and that enrichment would need to be global or at least widespread to distinguish it from natural geological variation. The Silurian hypothesis forces us to think about what traces would actually survive millions of years and be distinguishable as artificial. Frank and Schmidt identified several potential signatures that might persist in the geological record. None of them involve finding ancient artifacts or fossils. Instead, they're subtle chemical and isotopic anomalies that would require careful analysis to distinguish from natural variations. The first potential signature is a carbon isotope anomaly. When organisms use carbon for metabolism, they preferentially incorporate the lighter isotope carbon-12 over the heavier carbon-13. Fossil fuels, being derived from ancient organisms, are depleted in carbon-13 compared to inorganic carbon sources. When we burn fossil fuels, we release this isotopically light carbon into the atmosphere and oceans. This creates a measurable shift in the carbon-13 to carbon-12 ratio in the geological record. Ice cores and sediment cores from the industrial era show this shift clearly. The carbon isotope ratio began dropping in the late 1700s and has fallen dramatically since, coinciding precisely with increasing fossil fuel combustion. This is called the Suez effect, after the scientist who first described it. An ancient industrial civilization that burned fossil fuels would create a similar isotope anomaly in sediments from their time period. If we found a sediment layer showing a sudden depletion in carbon-13, followed by a return to normal ratios, that could indicate industrial fossil fuel use. The challenge is that natural processes can also shift carbon isotope ratios. Massive volcanic eruptions, changes in ocean circulation, variations in the global carbon cycle, all can affect the carbon-13 to carbon-12 ratio. To confidently attribute a carbon isotope anomaly to industrial activity, we'd need to rule out natural causes and find additional supporting evidence. We'd want to see the anomaly correlated with other signatures like changes in other isotope systems or enrichments of specific elements. A single line of evidence wouldn't be sufficient because geological systems are complex and many processes can create similar signals. The second potential signature involves nitrogen and phosphorus. Industrial agriculture uses massive amounts of fertilizer containing these elements. Modern runoff from agricultural areas has increased nitrogen and phosphorus delivery to oceans and lakes, creating eutrophication and dead zones. This increase in nutrient delivery would be recorded in sediments as elevated concentrations of nitrogen and phosphorus. An ancient agricultural civilization would similarly increase nutrient loading to aquatic systems. If we found a sediment layer with elevated nitrogen and phosphorus that couldn't be explained by natural processes like volcanic activity or changes in weathering rates, it might indicate ancient agriculture. Again, the challenge is distinguishing this from natural variation. Ocean circulation changes, continental weathering patterns, and biological innovation can all affect nutrient cycles. The third signature involves synthetic molecules that don't exist naturally. Modern industrial civilization has created thousands of synthetic chemicals, from pesticides to flame retardants to industrial solvents. Some of these molecules are extraordinarily persistent, surviving for decades or centuries in the environment. If molecules from an ancient industrial civilization persisted for millions of years, we might detect them in ancient sediments. The problem is that most synthetic organic molecules break down over thousands to millions of years. Chemical bonds are attacked by oxidation, radiation, and biological activity. Even the most persistent modern synthetic chemicals probably wouldn't survive recognizably for tens of millions of years. We might find chemical signatures suggesting unusual organic compounds, but proving they were synthetic rather than products of unusual natural chemistry would be difficult. The fourth potential signature is radioisotopes. If an ancient civilization developed nuclear technology, they would have produced artificial radioisotopes through fission reactions. Some of these isotopes have half-lives short enough that they'd be completely decayed after millions of years. But others have half-lives in the millions or billions of years and could still be detectable. Plutonium, 244 for example, has a half-life of 80 million years. If an ancient civilization produced significant quantities through nuclear reactors or weapons, traces might persist in sediments. Similarly, technetium-99, with a half-life of 211,000 years, could be detected if the ancient civilization was less than a few million years ago. The presence of these isotopes in concentrations or ratios that don't match natural production through cosmic rays or natural nuclear reactors would be strong evidence of artificial nuclear technology. Natural nuclear reactors have existed on Earth. The Oklo natural reactors in Gabon, Africa, operated about 2 billion years ago, when uranium concentrations and neutron moderation conditions allowed natural fission chain reactions to occur. These natural reactors produced some of the same isotopes artificial reactors create. So finding unusual isotope ratios isn't automatically proof of technology. We'd need to show the ratios couldn't be produced by natural reactors or other geological processes. The fifth signature involves climate change. Modern industrial civilization is dramatically altering Earth's climate through greenhouse gas emissions. This climate change is being recorded in ice cores, tree rings, sediment layers, and the distribution of species. An ancient industrial civilization would likely have caused similar climate perturbations, either through greenhouse gas emissions or other environmental modifications. The challenge is that Earth's climate has varied naturally throughout history. Ice ages, hothouse periods, rapid warming events all have occurred through natural causes. Distinguishing an ancient industrial climate perturbation from natural climate variation would require showing that the timing, magnitude, and pattern of change matched what we'd expect from industrial activity rather than natural forcing. We might look for rapid warming coinciding with carbon isotope anomalies, suggesting fossil fuel combustion. Or we might look for climate changes that don't correlate with known natural forcing mechanisms like orbital variations or volcanic activity. But Earth's climate system is complex, and we don't fully understand all the feedbacks and tipping points. Something that looks anomalous might just be a natural phenomenon we haven't recognized. The sixth potential signature is in the stratigraphic record itself. Modern humans are creating a distinct geological layer through our activities. We're moving enormous amounts of sediment through construction, mining, and agriculture. We're creating artificial materials like concrete and ceramics in vast quantities. We're altering the distribution of species through extinctions, invasions, and domestication. Future geologists would easily recognize the Anthropocene, the geological epoch of human dominance, as a distinct layer in the rock record. An ancient industrial civilization would create a similar stratigraphic signature. We'd expect to see a layer with unusual characteristics, perhaps containing concentrated metals, synthetic materials, or evidence of rapid environmental change. The layer might show signs of mass extinction as the civilization's activities stressed ecosystems. Above this layer, we'd expect recovery as ecosystems rebounded after the civilization collapsed or disappeared. Finding such a layer and proving it represented ancient industrial activity rather than natural catastrophes like asteroid impacts or massive volcanism would be challenging. We'd need multiple lines of evidence pointing to technological activity. A single anomalous layer wouldn't be convincing without additional signatures. The seventh signature involves biodiversity and extinction. Industrial civilization causes extinctions through habitat destruction, pollution, climate change, and direct exploitation. Modern species extinction rates are estimated to be 100 to 1,000 times higher than background rates. This mass extinction event would be visible in the fossil record as a sudden loss of species diversity, followed by gradual recovery. Ancient industrial civilizations might have caused similar extinction pulses. If we found a period of elevated extinction that couldn't be explained by known natural causes like asteroid impacts or volcanic flood basalts, it might indicate industrial activity. The challenge is that extinction rates vary naturally, and many factors can cause extinction pulses. Identifying one caused by technology rather than natural processes would require additional evidence. The fossil record shows 5 major mass extinctions and numerous smaller extinction events. Each has been attributed to natural causes: asteroid impacts, volcanism, climate change, ocean anoxia. Could any of these have been caused or exacerbated by ancient industrial civilizations? Probably not the major ones, which show clear evidence of natural triggers. But smaller extinction events, particularly those without clear natural causes, are harder to rule out completely. All of these potential signatures face the same fundamental challenge. Natural geological processes create enormous variability in the rock record. Chemical anomalies, isotope shifts, climate changes, extinction events, all occur naturally through various mechanisms. Distinguishing a technological signal from natural noise requires not just finding something unusual, but proving it couldn't have been produced naturally. This is why the Silurian hypothesis is so unsettling. It's not that we have evidence of ancient industrial civilizations. It's that the absence of evidence isn't particularly meaningful. If such civilizations existed more than a few million years ago, we might never find convincing proof unless we get extraordinarily lucky or develop new detection methods we haven't thought of yet. The hypothesis becomes even more disturbing when we consider how brief industrial civilization might be. Our species has had industrial technology for less than 3 centuries. If we collapse tomorrow through nuclear war, climate catastrophe, or some other existential risk, how long would our industrial signature be clearly visible? Within 1 million years, most direct evidence would be gone. Within 10 million years, even subtle chemical traces would be difficult to distinguish from natural variation. If industrial civilizations tend to be short-lived, lasting only centuries or millennia rather than millions of years, their signature in deep time would be extraordinarily faint. We'd be looking for a geological eye blink, a moment of unusual chemistry and rapid environmental change, buried in hundreds of millions of years of natural variation. Finding it would be like searching for a specific second in a century of video footage without knowing when to look. The question isn't just academic. It has profound implications for understanding technological life in the universe. If industrial civilizations are common but brief, leaving minimal traces, then the galaxy could have produced countless technological species that rose and fell without overlap. We might be one of many, separated by millions of years and light years, never directly encountering each other, but independently discovering similar physics and facing similar challenges. This connects to the Fermi paradox, the puzzle of why we haven't detected other technological civilizations despite the apparent likelihood of their existence. One resolution is that technological civilizations don't last long enough to overlap in time and space. They appear, flourish briefly, and vanish, leaving almost no trace for subsequent civilizations to find. If this is true for the galaxy, it might also be true for Earth itself across geological time. The Silurian hypothesis forces us to confront our ignorance about Earth's deep history. We know a lot about the past few million years. We have good fossil records, well-preserved sediments, and multiple proxies for climate and environment. But go back 50 million years, and our knowledge becomes fragmentary. Go back 100 million years, and whole chapters are missing. Go back 500 million years, and we're working with scattered pieces of a vast puzzle. We've found fossils from throughout this time period, and they show a progression of life forms that makes evolutionary sense. Simple organisms appear first, followed by increasing complexity, with humans arriving very recently. This progression strongly suggests we're the first technological species, at least on this planet. But the fossil record is so incomplete that we couldn't rule out brief technological episodes that left no fossils we've yet found. The hypothesis also highlights how much we don't know about our current impact on the planet. If we're trying to understand what traces an ancient civilization would leave, we need to understand what traces we're leaving. This requires studying the Anthropocene, the current geological epoch dominated by human activity. What signals are we creating that will be detectable millions of years from now? Some signals are obvious. The carbon isotope anomaly from fossil fuel burning will be clear in sediments. The presence of plutonium and other artificial radioisotopes from nuclear weapons testing will be detectable in sediment layers corresponding to the mid-20th century. The mass extinction currently underway will appear in the fossil record. The spread of domesticated species and invasive organisms will create unusual biogeographic patterns, but other signals are more subtle. We're altering the nitrogen cycle through fertilizer production. We're changing the phosphorus cycle through mining and agriculture. We're redistributing metals through mining and manufacturing. We're creating new minerals through industrial processes. All of these changes will leave traces, but will they be recognizable as technological rather than natural after millions of years? Understanding our own impact helps us understand what to look for when searching for ancient civilizations. If we know what chemical anomalies modern industry creates, we can search for similar anomalies in ancient sediments. If we understand how our activities affect extinction rates and species distributions, we can look for similar patterns in the fossil record. This search isn't just theoretical. Geologists and paleontologists are actively studying the Anthropocene to understand how human activity appears in the geological record. This research serves dual purposes: understanding our current impact on Earth systems and developing methods to detect technological signatures in deep time. Some researchers have begun examining ancient sediments, specifically looking for Silurian hypothesis signatures. They're not expecting to find evidence of ancient civilizations, but they're taking the hypothesis seriously enough to check. So far, no convincing evidence has been found. Every anomaly discovered has natural explanations or insufficient supporting evidence to claim technological origin. But the absence of findings is ambiguous. We've only examined a tiny fraction of the geological record in detail. Most sediment cores and rock outcrops have never been analyzed for the subtle chemical signatures an ancient civilization might leave. We're not conducting a systematic search because we don't have unlimited resources, and the prior probability of finding anything is considered very low. The prior probability judgment is important. Given what we know about evolution and the fossil record, it seems unlikely that another species reached industrial technology before humans. Intelligence appears to be rare in evolution. It required billions of years of evolution on Earth to produce one technological species. Having it happen twice seems improbable, unless intelligence is much more common than we think. But improbable isn't impossible. Evolution has produced complex adaptations many times, independently. Eyes evolved separately in different lineages. Flight evolved independently in insects, pterosaurs, birds, and bats. Echolocation evolved independently in bats and whales. If complex adaptations can evolve multiple times, could intelligence and eventually technology evolve more than once, given hundreds of millions of years? The counter-argument is that intelligence sufficient for technology seems to require a specific constellation of traits: large brains, manipulative appendages, social cooperation, communication abilities, and environmental pressures favoring innovation. This combination might be rare enough that it only happened once in Earth's history, despite the long timescales available. Moreover, if another species had reached industrial civilization millions of years ago, we'd expect the evolutionary progression to show signs of it. We'd expect to find fossils showing increasing brain size and tool use leading up to the technological period. The fossil record doesn't show any such progression except in the human lineage. This is strong evidence that we're the first. But this argument assumes the hypothetical ancient species left adequate fossils for us to have found. If they existed in small populations for geologically brief periods, we might not have their fossils. The absence of fossils isn't proof of absence given how incomplete the fossil record is. The Silurian hypothesis isn't claiming ancient industrial civilizations existed. It's making a more limited claim. If they had existed, we might not be able to detect them, and therefore we can't be completely certain they didn't exist based on the evidence available. This is different from saying they probably existed or that we should expect to find them. It's a statement about the limits of our knowledge and the incompleteness of the geological record. This distinction is important because the hypothesis is sometimes misunderstood as claiming ancient civilizations probably existed. That's not what Frank and Schmidt argued. They're pointing out an epistemological issue, a limit on what we can know about deep time. The geological record is good enough to tell us about the broad progression of life and environments, but it's not complete enough to rule out brief technological episodes with certainty. The practical implications are about how we search for biosignatures and technosignatures on other planets. If technological civilizations leave minimal traces after millions of years even on their home planets, detecting them on exoplanets will be extraordinarily difficult. We might be surrounded by dead civilizations whose ruins have been erased by geological processes, and we'd never know. This affects how we interpret data from Mars, which has a better preserved surface than Earth due to minimal tectonic activity. If we don't find evidence of past life or civilization on Mars, does that mean it never existed? Or just that we haven't looked in the right places, or that the evidence was destroyed? The Silurian hypothesis suggests we should be cautious about negative conclusions. The hypothesis also affects how we think about Earth's future. If industrial civilization collapses, what traces will we leave for future intelligent species that might evolve millions of years from now? Will they be able to discover that we existed? Or will geological processes erase us so thoroughly that they might face the same uncertainty we face about potential predecessors? These questions touch on something profound about existence and memory. We assume our civilization will be remembered, that our achievements and failures will be known to the future. But deep time is merciless. Given enough time, everything is forgotten, every trace erased, every monument ground to dust. The only way to ensure we're remembered is to persist, to survive long enough that our civilization spans geological timescales and becomes embedded in the planet's history in ways that can't be erased. The Silurian hypothesis is ultimately about humility. It reminds us that we don't know as much about Earth's history as we sometimes think. The geological record is a fragmentary text with missing pages and sections. We've done remarkable work reconstructing Earth's past from this incomplete record, but there are limits to what we can know with certainty. Those limits matter when we're asking fundamental questions about life, intelligence, and technology in the universe. If we can't be completely certain we're the first technological species on our own planet, how can we be certain about what's happened on billions of other planets over billions of years? The universe might be full of risen and fallen civilizations whose existence is now undetectable. This is the unsettling possibility the Silurian hypothesis forces us to confront. We might not be first. We might be the latest in a long series, separated by millions of years from predecessors whose very existence has been erased by the planet we share. The evidence for this is absent. But absence of evidence is not evidence of absence when the evidence would be this difficult to find. In the next chapter, we'll examine in detail what actually happens to evidence over geological time. How do different materials and structures degrade? What processes destroy or preserve information? How complete or incomplete is the geological record really? Understanding these mechanisms is crucial for evaluating whether ancient civilizations could hide in deep time and what traces, if any, might still be detectable today. The rock beneath your feet is not a permanent record. It's a palimpsest, written and erased and rewritten countless times over billions of years. Understanding what survives this constant recycling and what gets destroyed is crucial for evaluating whether traces of an ancient industrial civilization could persist in the geological record. The answer is more complex than simply saying things decay over time. Some materials and structures survive for billions of years while others vanish in centuries. The preservation of evidence depends on what it's made of, where it's located, and what geological processes affect it. This chapter explores the harsh reality of deep time and reveals why the Earth is simultaneously the best and worst place to search for evidence of ancient technological life. Geological preservation operates on principles that often contradict our everyday experience with materials and artifacts. In human timescales, metal seems permanent, while organic matter decays quickly. Stone structures outlast wooden ones. Glass is durable, while paper is fragile. These intuitions fail completely when extended to millions of years. On geological timescales, the rules change. Location matters more than composition. Burial depth determines survival better than material strength. And paradoxically, some of the most advanced human materials are among the least likely to survive deep time. Let's start with the most optimistic scenario for preservation. What would happen to a modern city if humans suddenly vanished and geological processes were allowed to operate without interference for 10 million years? This thought experiment reveals how effectively Earth erases surface features. In the first year after abandonment, wooden structures begin rotting. Roofs leak, allowing water to penetrate buildings. Metal corrodes where exposed to moisture and oxygen. Plants colonize cracks in pavement. Without maintenance, infrastructure deteriorates rapidly. Roads develop potholes as freeze-thaw cycles break up asphalt. Bridges begin to rust and weaken. Within a decade, most wooden buildings have collapsed. Vegetation has overgrown streets and parks. Trees grow through foundations and buckle pavement. Rivers that were channelized begin to meander naturally, flooding areas that were kept dry by human engineering. Coastal structures erode as waves and storms attack them, without repair. Within a century, nearly all surface structures have collapsed. Steel-framed skyscrapers might remain partially standing, but they're rusting hulks. Concrete is cracking and spalling as reinforcing steel corrodes and expands. Glass has shattered or fallen from window frames. The urban landscape is recognizable as ruins, but it's already transitioning back to nature. Within 1,000 years, even the most robust structures have fallen. The ruins are being buried by sediment in some locations, particularly river valleys and coastal areas. In other locations, erosion is removing the rubble entirely. The outlines of cities might still be visible from the air as vegetation patterns or subtle topographic features, but nothing resembling intact buildings remains. Within 10,000 years, glaciation has occurred in some regions if the climate has shifted toward ice age conditions. Glaciers are extraordinarily effective at erasing surface features. A continental ice sheet, thousands of meters thick flowing over a city, would pulverize everything, grinding buildings to powder and carrying the debris hundreds of kilometers away. Even without glaciation, 10,000 years of erosion has substantially modified the landscape. Within 100,000 years, most surface traces are gone in actively eroding regions. River valleys have shifted course multiple times, reworking sediment. Coastlines have migrated as sea level fluctuated with climate cycles. Mountains are eroding at rates of meters per 1,000 years in active orogens. Only in areas of deposition or extreme aridity might substantial traces remain at the surface. Within 1 million years, plate tectonics begins to significantly affect the evidence. Subduction zones are consuming oceanic crust at rates of several centimeters per year. This means about 10 to 20 kilometers of lateral motion, potentially carrying coastal cities into subduction zones or moving them relative to ancient shorelines. Continental collision zones are uplifting mountains, bringing deep rocks to the surface while burying surface rocks beneath thrust sheets. Within 10 million years, our target time frame, the transformation is complete. In most locations, nothing surface level survives. Oceanic crust containing any cities built on islands or continental margins has been subducted into the mantle and melted. Continental locations have undergone millions of years of erosion or burial. The landscape has been completely reshaped by geological processes. What might survive this destruction? The answer is counterintuitive. Things buried deep underground and things dispersed widely rather than concentrated. Deep mines, underground storage facilities, and foundations extending deep into bedrock have the best chance of preservation. These features are protected from surface erosion and might survive until tectonic processes affect them. But even deep underground features face destruction. If the region undergoes mountain building, the rocks containing these features will be metamorphosed, heated, and compressed until their structure is altered beyond recognition. A mine shaft in rock that gets subducted or deeply buried will be crushed and deformed as the rock flows plastically under pressure. The void will close, the tunnel walls will merge, and any artifacts within will be compressed and altered. Metamorphism is particularly effective at destroying evidence. When rocks are subjected to temperatures above 300 to 400 degrees Celsius, and pressures equivalent to being buried 10 to 20 kilometers deep, their mineralogy changes. Clays transform into micas and garnets. Organic material is converted to graphite. Fossils are destroyed as their delicate structures recrystallize. Any technological artifacts would similarly be altered beyond recognition. The type of metamorphism matters. Low-grade metamorphism at relatively shallow depths and moderate temperatures might preserve some structural features even while changing mineralogy. High-grade metamorphism approaching partial melting destroys everything. Rocks that have been metamorphosed to granulite or eclogite facies, conditions existing at 25 to 50 kilometers depth, retain no information about their pre-metamorphic state except bulk chemistry. Even without metamorphism, deep burial changes rocks through diagenesis. The physical and chemical changes that occur as sediment is compacted and lithified. Pore spaces are eliminated as grains are pressed together. Minerals dissolve and reprecipitate, cementing the rock. Organic material is broken down by heat and pressure, eventually becoming oil or gas if conditions are right, or simply dissipating as small molecules. any technological materials buried in sediment would experience the same processes. Metals would oxidize and corrode if oxygen was present. In anoxic conditions, metals might persist longer but would still react with sulfur, forming sulfides, or with other elements present in the sediment. Over millions of years, even noble metals like gold would migrate through the rock as atoms dissolve in groundwater and reprecipitate elsewhere. Plastics, the signature material of modern civilization, would degrade through multiple mechanisms. Ultraviolet light breaks down plastic at Earth's surface, but buried plastic is protected from UV. However, heat and pressure from burial would break the long polymer chains into smaller molecules. Bacterial action would degrade some plastics, though not all. After millions of years, most plastics would be reduced to hydrocarbon molecules indistinguishable from naturally occurring organic compounds in the rock. Some particularly stable plastics might persist as identifiable molecules for longer. Polytetrafluoroethylene, known as Teflon, is extraordinarily resistant to degradation. In the absence of extreme heat, it might survive for millions of years, but it would be present in such small quantities and so widely dispersed that detecting it would be extraordinarily difficult. A few molecules of unusual fluorinated hydrocarbons scattered through a sedimentary layer wouldn't stand out without specifically looking for them. Concrete, one of humanity's most widely used materials, weathers on timescales of decades to centuries at Earth's surface. Buried concrete might last longer, protected from freeze-thaw cycles and chemical weathering. But on million-year timescales, concrete would gradually dissolve and recrystallize. The calcium carbonate cement would dissolve in slightly acidic groundwater and reprecipitate elsewhere. The aggregate would remain, but it would be indistinguishable from natural sediment. Glass is more durable than concrete in some ways. Volcanic glass, obsidian, survives for millions of years in the geological record. But human glass is different from natural volcanic glass in composition and structure. Industrial glass contains additives that make it less stable over long periods. Buried glass would gradually devitrify, crystallizing into microcrystalline minerals. After millions of years, it might be recognizable as having once been glass, but its origin as manufactured rather than volcanic glass would be hard to prove. Ceramics and fired clay have better preservation potential. Ancient pottery survives from thousands of years ago, and ceramic materials can persist for millions of years, if not subjected to metamorphism. The problem is distinguishing manufactured ceramics from natural clay-rich sediments that have been baked by contact with igneous intrusions. Both produce similar mineral assemblages. Without diagnostic features like tool marks or shapes that couldn't occur naturally, ancient ceramics might be mistaken for metamorphosed sedimentary rock. What about the most durable materials? Diamond is essentially eternal on geological timescales, unless subjected to conditions that convert it back to graphite. But industrial diamonds are tiny and would be incredibly rare in sedimentary rocks. Finding them would require processing vast amounts of rock and somehow distinguishing industrial diamonds from natural diamonds, which is difficult because both have similar properties. Tungsten carbide, used in drill bits and cutting tools, is extremely hard and chemically resistant. It might survive for millions of years, but again in tiny quantities widely dispersed. Detecting unusual concentrations of tungsten in ancient sediments might indicate former industrial activity, but it would be hard to prove the tungsten was from technological sources rather than natural hydrothermal enrichment. Radioactive waste, if buried in geological repositories as planned, might be the most enduring signature of industrial civilization. Spent nuclear fuel contains plutonium and other transuranic elements with half-lives of thousands to millions of years. These elements don't occur naturally on Earth in significant quantities. Finding them in ancient rocks would be strong evidence of nuclear technology. However, this evidence would only exist if the ancient civilization used nuclear power and buried the waste in repositories that survived to the present. If they didn't develop nuclear technology, or if the waste was stored in facilities that were subsequently destroyed by erosion or subduction, no trace would remain. And natural nuclear reactors, like the Oklo reactors that operated 2 billion years ago, complicate interpretation by showing that unusual isotope ratios can occur naturally. The isotope ratios in spent nuclear fuel are different from those in natural uranium deposits, so careful analysis could distinguish them. But after millions of years of radioactive decay and potential migration of daughter isotopes, the signature might be degraded enough to be ambiguous. You'd need to find the repository intact with concentrated radioactive waste, showing impossible isotope ratios to be certain of technological origin. Beyond physical artifacts, what about chemical signatures? This is where the preservation picture becomes more nuanced. Some chemical signals can persist for hundreds of millions of years in the right conditions, while others disappear in thousands of years. Carbon isotopes, crucial for the Silurian hypothesis, are recorded in organic matter and carbonate minerals. When organisms die, their carbon isotope ratios reflect the carbon sources they used during life. Plants discriminate against carbon-13 during photosynthesis, so organic matter is depleted in carbon-13 compared to atmospheric carbon dioxide. Fossil fuels, derived from ancient organic matter, retain this depletion. When fossil fuels burn, the isotopically light carbon enters the atmosphere and is incorporated into new organic matter and carbonates. This creates a negative carbon isotope excursion, a period when carbon-13 to carbon-12 ratios drop suddenly. The modern industrial excursion is clearly visible in ice cores and recent sediments. Would this signal survive millions of years? It depends on what happens to the carbon. If organic matter is buried and preserved in sedimentary rocks, the isotope ratio will be retained for hundreds of millions of years. We can measure carbon isotopes in organic matter from Paleozoic rocks over 300 million years old. The isotopes are stable and don't change unless the rock is metamorphosed or the organic matter is destroyed. But there's a catch. Carbon isotope ratios vary naturally for many reasons. Changes in ocean circulation, the distribution of photosynthetic organisms, volcanic activity, and weathering rates all affect the global carbon cycle and can create isotope excursions. Distinguishing a technological signal from natural variation requires showing that the excursion has characteristics that don't match natural processes. The modern industrial excursion has a specific signature. It's rapid, occurring over centuries rather than millennia. It's large, about 2 per mil shift in delta carbon-13, and it's global, affecting both terrestrial and marine environments simultaneously. An ancient industrial excursion might show similar features, but proving it was technological rather than a rapid natural event would require additional evidence. Nitrogen isotopes provide another potential signature. Industrial nitrogen fixation for fertilizer production has altered the nitrogen cycle, increasing the amount of reactive nitrogen in the environment. This affects nitrogen isotope ratios in sediments. Natural nitrogen fixation by bacteria also affects isotope ratios. But the modern anthropogenic signal is large and rapid enough to be distinguishable. An ancient civilization using nitrogen fertilizers might create a similar signal. However, Nitrogen isotopes are more susceptible to alteration during diagenesis than carbon isotopes. Nitrogen in organic matter can be lost or modified as rocks are buried and heated. After millions of years, the nitrogen isotope record might be degraded enough to be uninterpretable. Sulfur isotopes are affected by industrial activity through the burning of fossil fuels containing sulfur. Coal and oil have characteristic sulfur isotope ratios related to the ancient environments in which they formed. Burning them releases sulfur with those ratios into the atmosphere. This sulfur eventually deposits in sediments, creating an isotope signal. Natural processes also affect sulfur isotopes through bacterial sulfate reduction, volcanic emissions, and weathering of sulfide minerals. An industrial sulfur isotope signal would need to be distinguished from these natural variations. The combination of sulfur and carbon isotope anomalies occurring together might be more diagnostic than either alone. Strontium isotopes record continental weathering rates. When silicate rocks weather, they release strontium with an isotope ratio reflecting the age and composition of the rocks being eroded. This strontium enters the ocean and is incorporated into marine carbonates. Changes in weathering rates or the source of weathered material affect the strontium isotope composition of seawater. Industrial activity increases weathering rates through mining, agriculture, and land disturbance. This might shift strontium isotopes in a detectable way. However, natural climate changes and tectonic events also affect weathering rates, making it difficult to identify an industrial signal uniquely. Lead isotopes might provide stronger evidence. Natural lead has 4 stable isotopes with ratios determined by radioactive decay of uranium and thorium over geological time. Industrial lead, particularly from gasoline additives and smelting, has been released into the environment with isotope ratios reflecting the ore deposits from which it was extracted. These industrial lead signatures are clearly visible in recent sediments and ice cores. They represent artificial redistribution of lead with specific isotope ratios that don't match local natural background. An ancient civilization smelting lead ore and dispersing it globally might create a detectable lead isotope anomaly in sediments. The challenge is that lead is mobile during diagenesis. It can be leached from sediments by acidic groundwater and redeposited elsewhere. After millions of years, the original depositional isotope ratios might be overprinted by later lead migration. Only in depositional environments that remained chemically stable, such as deep ocean sediments that didn't experience significant diagenesis, might the original signal be preserved. Platinum group elements offer another potential signature. These elements are extremely rare in Earth's crust, but are used in catalytic converters, electronics, and other industrial applications. Modern emissions from vehicle exhaust and industrial processes have enriched platinum group elements in recent sediments, particularly near urban areas. An ancient civilization using similar technologies might create a global or regional enrichment of platinum group elements. These elements are chemically stable and wouldn't be destroyed by diagenesis, though they might be redistributed. Finding a sedimentary layer enriched in platinum, palladium, rhodium, and iridium in ratios that don't match meteoritic or mantle sources could indicate technological activity. However, there's an ambiguity problem. Asteroid impacts also enrich sediments in platinum group elements. The famous iridium anomaly marking the Cretaceous-Paleogene boundary, associated with the asteroid impact that helped kill the dinosaurs, shows how impacts create similar signatures. Distinguishing a technological enrichment from an impact would require additional evidence, such as absence of shocked quartz and other impact indicators. Rare earth elements are used extensively in modern technology for electronics, magnets, and catalysts. Their distribution in sediments might be altered by industrial activity. Different rare earth elements are used in different ratios for various applications. An unusual rare earth element pattern that doesn't match natural fractionation processes could indicate technology. Natural processes fractionate rare earth elements in characteristic ways. Weathering, hydrothermal activity, and biological uptake each create specific patterns. A technological pattern would need to be distinguishable from these natural signatures. This might be possible if the ancient civilization concentrated specific rare earth elements in ways nature doesn't. Organic molecules provide another category of potential signatures. Modern industrial civilization has synthesized thousands of novel organic compounds, from pharmaceuticals to pesticides to plastics. Some of these molecules are extraordinarily persistent in the environment. Polychlorinated biphenyls, once widely used in electrical equipment, persist for decades to centuries. Fluorinated compounds like PFAS are even more persistent. Would these molecules survive millions of years? Almost certainly not in their original form. Chemical bonds break down over time due to thermal energy, radiation, and chemical reactions. The most stable organic molecules known from the geological record are certain biomarker compounds that survive for hundreds of millions of years. But even these are eventually destroyed or altered beyond recognition. However, the degradation products of synthetic molecules might persist. When complex organic molecules break down, they produce simpler compounds that might have unusual structures not commonly found in nature. Detecting a suite of organic compounds with structures suggesting synthetic origin could indicate ancient technology. The problem is distinguishing unusual natural organic chemistry from technological synthesis. Nature produces incredibly diverse organic molecules through biological and geological processes. Some natural products have structures as complex as synthetic compounds. Without knowing specifically what to look for, identifying technological organic compounds in ancient sediments would be extremely difficult. Microplastics represent a specific category of persistent organic signature. Modern oceans and sediments contain vast quantities of plastic particles ranging from millimeters to micrometers in size. These particles are accumulating in marine sediments and will be incorporated into sedimentary rocks. Over geological time, microplastics will degrade. The polymer chains will break down through thermal and chemical processes. But this degradation might take millions of years in anoxic buried sediments. The products might include unusual hydrocarbon molecules with characteristics suggesting polymeric origin. Detecting ancient microplastics would require finding particles with morphologies suggesting manufacturing, perhaps spherical beads or fibers, made of organic polymers with unusual chemical structures. After millions of years, such particles might be rare and altered, but some fraction might survive in favorable depositional environments like anoxic deep ocean sediments. What about biological signatures? A technological civilization would alter the biosphere in detectable ways. Mass extinction, introduction of invasive species, domestication of plants and animals, all would affect the fossil record and might be distinguishable from natural biological changes. The current mass extinction caused by human activity will be visible in the fossil record as a rapid loss of species diversity. The simultaneous extinction of large vertebrates on different continents, the spread of commensal species like rats and certain plants globally, and the appearance of domesticated species in fossil assemblages far from their native ranges would all indicate intelligent intervention. An ancient civilization would create similar patterns. We'd expect to see a period of elevated extinction rates, particularly affecting large vertebrates and specialist species. We'd see biogeographic anomalies with species appearing in locations they couldn't reach naturally. We'd potentially see morphological changes in certain species consistent with domestication. The challenge is distinguishing this from natural extinction events and biogeographic changes. Species extinctions occur naturally. Continental drift and changing sea levels alter species distributions. Some natural events cause rapid extinction pulses that might resemble technological impacts. We'd need multiple lines of evidence to confidently attribute an extinction event to technology. The extinction pattern would need to be inconsistent with known natural causes. It should coincide with other technological signatures, like chemical anomalies or isotope excursions. And ideally, we'd see evidence of post-extinction recovery, showing ecosystem reorganization, consistent with removal of a dominant, disturbing force. The fossil record of the species itself is another consideration. A technological species would presumably leave fossils, though not necessarily many if their population was small and their existence brief in geological terms. Their fossils might show characteristics indicating intelligence, large brain cases, morphological adaptations for manipulation, evidence of tool use through wear patterns on bones or teeth. But what if we haven't recognized these fossils? The hominid fossil record is quite sparse, with many species known from only a few specimens. If another intelligent lineage existed millions of years earlier with a similarly sparse fossil record, we might not have found their remains yet, or we might have found them but not recognized their significance. Paleontologists identify species based on morphology. An ancient intelligent species might not have obvious markers of intelligence in their skeletal structure. Brain size can be estimated from skull capacity, but intelligence doesn't correlate perfectly with brain size. Tool use might not leave clear traces on bones unless the tools were used intensively over long periods. The absence of fossils showing a progression toward intelligence in any lineage except hominids is the strongest evidence against ancient technological species. We see increasing brain size and tool use in the hominid lineage over millions of years. No other lineage shows similar trends. This suggests intelligence sufficient for technology evolved only once, but evolution can be rapid under strong selective pressure. If conditions favored intelligence for a relatively brief period, a species might evolve technological capability relatively quickly without leaving an extensive fossil record of the transition. This seems unlikely, but cannot be ruled out entirely, given the incompleteness of the fossil record. Preservation also depends on environment. Most fossils come from marine or lacustrine environments where sedimentation occurs. Terrestrial organisms fossilize much less frequently unless they die in rivers, lakes, or other depositional settings. A technological species might have lived primarily in terrestrial environments that don't preserve fossils well, further reducing the chances we'd find their remains. Geographic sampling bias affects what we find. Most paleontology occurs in North America, Europe, and parts of Asia, where there are many researchers and good outcrop exposure. Large regions of Africa, South America, and other continents remain poorly studied. A species whose range didn't overlap heavily with well-studied regions might not have been discovered yet. Temporal sampling bias is equally important. Certain time periods are much better represented in the geological record than others. The Cretaceous period has extensive sedimentary rocks and is well studied. The Triassic is less well represented. The Permian even less so. An ancient civilization existing during a poorly represented time period would be much harder to detect. The deep ocean represents a particularly challenging environment for preservation and discovery. If an ancient civilization lived on oceanic islands or coastal regions that are now subducted, all physical evidence would be destroyed. We can only access ocean crust younger than about 200 million years. Anything older has been recycled into the mantle. This creates a detection blind spot. Any civilization existing more than 200 million years ago in regions that are now oceanic has left no physical trace we can access. Their cities, artifacts, and even chemical signatures might have been subducted and melted. Only signals that spread globally into continental sediments might survive. Even on continents, subduction can destroy evidence. Coastal regions undergo accretion and erosion as oceanic crust subducts beneath continental margins. Sediments are scraped off the descending plate and added to the continent. But this process is violent and destructive. Rocks are deformed, metamorphosed, and partially melted. Any evidence in coastal sediments might be destroyed during accretion. Mountain building similarly destroys evidence. When continents collide, the rocks at the collision zone are intensely deformed, heated, and uplifted. The Himalayas are being built by the collision of India and Asia. The rocks being uplifted have been metamorphosed and deformed. Any evidence preserved in those rocks before collision would likely be destroyed or rendered unrecognizable. Yet some information survives even intense metamorphism. Certain mineral inclusions, particularly zircons, are nearly indestructible and retain information about their formation conditions even when the surrounding rock is completely altered. These inclusions might preserve chemical signatures or isotope ratios indicating technological activity, even if all other evidence is destroyed. The survival of information also depends on what kind of information we're seeking. Physical artifacts are fragile and unlikely to survive tens of millions of years. Chemical signatures are more robust but can be degraded or overprinted. Isotopic signatures are the most durable, potentially surviving hundreds of millions of years if the rocks aren't too severely metamorphosed. This hierarchy of preservation means our best chance of detecting ancient civilizations is through isotopic and chemical anomalies rather than physical artifacts. We shouldn't expect to find ancient tools or structures. We should search for unusual patterns in the geochemistry of sedimentary rocks, signatures that can't be explained by natural processes alone. But this approach has low statistical power. Chemical and isotopic variations in rocks are substantial. Natural processes create enormous variability. To detect a technological signal above this natural background requires either a very strong signal or very precise measurements, coupled with good models of natural variability. We lack comprehensive surveys of isotopic and chemical variations in sedimentary rocks throughout geological time. We have measurements from specific localities and time periods, usually chosen for other research purposes. A systematic search for Silurian hypothesis signatures would require measuring many different geochemical parameters in sediments spanning Earth's entire history, a massive undertaking. Even if such a survey were conducted, interpreting the results would be challenging. Every anomaly would need to be evaluated for potential natural causes. Given how many natural processes affect geochemistry, most anomalies would probably have mundane explanations. Only a combination of multiple independent anomalies occurring together might constitute convincing evidence. The null hypothesis that no ancient industrial civilizations existed is strongly favored by prior probability. Evolution appears to have produced technological intelligence only once. The fossil record shows a clear progression in the hominid lineage, with no comparable progression in other lineages. The absence of obvious technological signatures in the geological record is consistent with no ancient civilizations. To overturn this null hypothesis would require extraordinary evidence. Multiple independent signatures that can't be explained naturally, occurring together in time and ideally in space. A single carbon isotope anomaly wouldn't suffice. But carbon, nitrogen, and sulfur isotope anomalies coinciding with rare earth element enrichments, platinum group element patterns, and biogeographic disruptions might be enough to warrant serious consideration. No such constellation of evidence has been found. This doesn't prove ancient civilizations didn't exist, but it means we have no positive evidence for them. The Silurian hypothesis remains a logical possibility, rather than a supported theory. The geological record could hide ancient civilizations, but currently doesn't show signs of doing so. In the next chapter, we'll examine specific types of signatures in more detail, exploring what they would look like, how we'd detect them, and what natural processes might mimic them. We'll look at nuclear signatures, chemical anomalies, and biological disruptions, evaluating each as a potential marker of ancient technology. The question isn't just whether these signatures could survive, but whether we'd recognize them if we found them, and whether we could distinguish them from the countless natural processes that create similar signals. The geological record is a harsh filter. It preserves only tiny fractions of what once existed, but some information survives even the most destructive processes. The question is whether technological signatures are among the durable markers that can persist across tens of millions of years, and whether we're looking in the right places with the right tools to detect them. The search for evidence of ancient industrial civilizations requires us to think like forensic investigators working a cold case that's millions of years old. The crime scene has been contaminated, cleaned, and rebuilt countless times. The witnesses are extinct. The physical evidence has mostly been destroyed. What remains are faint chemical traces, statistical anomalies, and patterns that might mean everything or nothing. In this chapter, we'll examine the specific signatures that might persist in the geological record and the detective work required to distinguish genuine technological markers from the overwhelming noise of natural processes. The challenge isn't just finding something unusual. It's proving that what you found couldn't possibly be natural, and that's far harder than it sounds. Nuclear signatures represent perhaps the strongest potential evidence for ancient technological civilizations. Nuclear technology produces isotopes and isotopic ratios that simply don't exist in nature, or exist in ratios so different from natural production that they constitute unmistakable markers. If we found these signatures in ancient rocks, the case for technology would be compelling. The question is what to look for and where to look for it. Modern nuclear technology produces several categories of artificial isotopes. Fission products are created when uranium or plutonium nuclei split, producing lighter elements like cesium, strontium, and iodine in isotopic forms that don't occur naturally or occur only in trace amounts. Activation products are created when neutrons from fission reactions strike other materials, transforming stable isotopes into radioactive ones. Transuranic elements like plutonium, americium, and curium are created when uranium absorbs neutrons without fissioning. Each category has different preservation potential. Short-lived fission products like iodine-131, with a half-life of 8 days, would be completely decayed within months. They wouldn't survive long enough to be detectable in geological materials. Intermediate half-life isotopes like cesium-137, with a half-life of 30 years, would be gone within a few centuries. Only long-lived isotopes have any chance of detection across millions of years. Plutonium-239 has a half-life of 24,000 years. After 10 million years, it would have undergone over 400 half-lives of decay, reducing any original amount to essentially zero. Even starting with kilogram quantities, after 10 million years you'd have less than individual atoms remaining. Plutonium-239 can't be detected from ancient civilizations millions of years old, but plutonium-244 has a half-life of 80 million years. This isotope is produced in small quantities in nuclear reactors through multiple neutron captures. After 10 million years, it would have decayed by about 12%. Starting quantities would still be substantially present. If an ancient civilization used nuclear reactors extensively and concentrated plutonium-244 in waste repositories, we might detect it today. The problem is that plutonium-244 doesn't exist naturally on Earth in measurable quantities. Its long half-life means some existed when Earth formed 4.5 billion years ago, but it's all decayed by now. Finding any plutonium-244 in rocks would be extraordinary and would demand explanation. Natural production through cosmic ray interactions is possible, but produces only infinitesimal amounts. If we found a rock containing plutonium-244 at concentrations above what cosmic rays could produce, we'd need to determine whether it came from nuclear technology or from natural nuclear reactors. The Oklo natural reactors in Gabon operated about 2 billion years ago, sustained by unusually high uranium concentrations and specific groundwater conditions. These natural reactors produce plutonium through the same neutron capture processes that occur in artificial reactors. Distinguishing artificial from natural reactor products requires analyzing the full suite of isotopes and their ratios. Natural reactors operate under specific conditions that produce characteristic isotope patterns. Artificial reactors, especially modern ones optimized for power production or plutonium production, create different patterns. The ratio of plutonium-239 to plutonium-240, the amounts of americium and curium, the fission product distributions, all vary depending on reactor conditions. An ancient artificial reactor would have its own signature, potentially different from both modern reactors and natural reactors. If the ancient civilization used reactor designs unlike ours, the isotope patterns might not match any known signatures. This creates an identification problem. How do we recognize an unknown technological signature when we don't know what it should look like? The solution involves looking for patterns that can't be produced by any known natural process, even if they don't match modern technology exactly. Certain isotope ratios are impossible to create without concentrated neutron fluxes. Certain combinations of transuranic elements can't form through cosmic ray interactions. Finding these impossible signatures would indicate technology even if the specific patterns are unfamiliar. Technetium provides another potential signature. All technetium isotopes are radioactive, with the longest lived being technetium-98, with a half-life of 4.2 million years. No natural process on Earth produces technetium in measurable quantities because there's no stable isotope to act as a reservoir. Any technetium in Earth's crust has decayed completely since the planet formed. Nuclear reactors produce technetium-99 as a fission product. It has a half-life of 211,000 years, meaning it would be substantially decayed after 10 million years, but potentially still detectable if originally present in large quantities. Finding technetium-98 or 99 in ancient rocks would be strong evidence of nuclear technology. because there's no natural source. The challenge is detection sensitivity. Technetium would need to be measured at extraordinarily low concentrations if it came from millions of years ago. Modern analytical techniques using mass spectrometry can detect individual atoms of specific isotopes, so the sensitivity exists. But analyzing every sediment layer looking for technetium would be impractical. We'd need some reason to look at specific layers, perhaps based on other anomalies. Uranium isotope ratios provide another line of evidence. Natural uranium consists of uranium-238, uranium-235, and uranium-234 in specific ratios determined by radioactive decay. Uranium-235 has been decaying faster than uranium-238 because of its shorter half-life, so the ratio of uranium-235 to uranium-238 has decreased over Earth's history. We can calculate what this ratio should be at any point in the past. Nuclear reactors preferentially consume uranium-235 because it's more easily fissionable. Enrichment processes for reactor fuel concentrate uranium-235, while depleted uranium left over is heavily enriched in uranium-238. If an ancient civilization mined uranium, enriched it, and disposed of depleted uranium, we might find uranium deposits with impossible isotope ratios. The Oklo natural reactors show this signature. The uranium ore at Oklo has depleted uranium-235 ratios because natural fission reactions consumed it preferentially. But the depletion pattern at Oklo is consistent with natural reactor operation, given the geological conditions. Artificial depletion would potentially show different patterns, particularly if the enrichment process separated isotopes before fission occurred. Finding uranium ore with uranium-235 depletion that can't be explained by natural reactors and occurred at a time when natural reactors couldn't operate would indicate technology. Natural reactors require specific conditions: high uranium concentration, proper neutron moderation by water, and absence of neutron-absorbing elements. These conditions existed 2 billion years ago when uranium-235 was more abundant, but they wouldn't exist for much of Earth's history. If we found uranium depletion in rocks from a time period when natural reactors were impossible, it would suggest artificial use. The uranium would need to be depleted beyond what any natural process could cause, with patterns consistent with enrichment technology. This would be difficult to fake through natural processes. Tritium, the radioactive isotope of hydrogen, has a half-life of only 12 years. It can't survive from ancient times. But tritium production through nuclear reactions would have created helium-3 as a decay product. Helium-3 is stable and would persist indefinitely. Natural helium consists mostly of helium-4, with only trace amounts of helium-3. Finding localized enrichments of helium-3 might indicate former tritium production. However, helium-3 is also produced naturally by decay of tritium from cosmic rays and by release from Earth's mantle. Distinguishing technological helium-3 from natural sources requires finding it in contexts where natural production is unlikely, perhaps concentrated in sediments associated with other nuclear signatures. The search for nuclear signatures faces a fundamental challenge: where to look. Nuclear waste repositories or reactor sites would be the most likely places to find concentrated signatures, but we don't know where ancient sites would be located. They might be subducted, eroded away, or buried under kilometers of younger rock. Without knowing where to look, we'd need to survey vast numbers of rock samples, an impractical undertaking. One approach is to focus on sedimentary rocks that accumulated in marine or lacustrine environments. These rocks receive sediment from wide geographic areas through river transport. If an ancient civilization used nuclear technology and released radioactive materials to the environment, some would have been transported to depositional basins and preserved in sediments. The signature would be diluted through mixing with natural sediments, but it might still be detectable as a small anomaly in isotope ratios or trace element concentrations. We'd look for layers showing slight enrichments in elements like technetium, or unusual uranium isotope ratios, or elevated plutonium that can't be explained by cosmic ray production. This approach requires analyzing many samples at high precision to detect small anomalies. Current geological surveys don't routinely measure these isotopes because they're not expected to be present and the analyses are expensive. A dedicated search would require significant resources with low probability of finding anything. Chemical signatures beyond nuclear markers offer another category of potential evidence. Industrial chemistry produces and releases vast quantities of synthetic compounds and redistributes elements in ways that don't occur naturally. Some of these chemical fingerprints might persist in the geological record. Chlorinated organic compounds represent one category. Modern industry produces chlorinated pesticides, solvents, and industrial chemicals. Many are persistent in the environment, resisting degradation for decades or longer. Polychlorinated biphenyls, once widely used in electrical equipment, persist for centuries in sediments. Dioxins, formed as byproducts in various industrial processes, are extremely stable. Over millions of years, these compounds would eventually degrade. Chemical bonds are attacked by oxidation, radiation, and thermal energy, but the degradation might leave traces. Unusual chlorinated hydrocarbon fragments in ancient sediments could indicate former presence of synthetic chlorinated compounds. The challenge is distinguishing these from natural chlorinated organics produced by marine organisms and geological processes. Some marine algae produce chlorinated compounds. Volcanic processes can create chlorinated organics through reactions between hydrocarbons and chlorine-rich fluids. Forest fires produce chlorinated aromatics. A technological signature would need to show chlorination patterns or molecular structures that don't match any natural source. Fluorinated compounds are less common naturally. Nature produces very few organofluorine compounds, while industry produces thousands. Per- and polyfluoroalkyl substances, known as PFAS, are extraordinarily persistent because carbon-fluorine bonds are among the strongest in chemistry. PFAS contamination is now global, present in rain, snow, and remote locations, far from sources. If PFAS or similar fluorinated compounds survived millions of years, they'd be smoking guns for technology. The carbon-fluorine bond is so strong that these molecules might survive much longer than other organics. Finding fluorinated organics with structures consistent with industrial synthesis in ancient sediments would be powerful evidence. But would PFAS really survive millions of years? In anoxic buried sediments at modest temperatures, possibly. High temperatures during deep burial would eventually break even carbon-fluorine bonds, and the concentrations would be extremely low after millions of years of dilution and degradation. Detecting them would require extraordinarily sensitive analytical methods. Rare earth element patterns provide another potential signature. These elements are used extensively in modern technology for magnets, phosphors, catalysts, and electronics. Different technologies use rare earth elements in different proportions. Neodymium for magnets, europium and terbium for phosphors, lanthanum and cerium for catalysts. Natural processes fractionate rare earth elements in characteristic ways. Weathering preferentially mobilizes light rare earth elements over heavy ones. Hydrothermal systems create specific patterns. biological uptake shows distinct preferences. A technological pattern would need to differ from all natural fractionation processes. Modern electronics waste being released to the environment creates unusual rare earth element patterns in some sediments. If an ancient civilization used rare earth elements and disposed of waste improperly, we might find sediment layers with rare earth element distributions that don't match natural processes. The pattern would need to be distinctly technological, showing enrichments and ratios impossible to create through weathering, hydrothermal activity, or biological fractionation. Platinum group elements also have technological applications. Platinum, palladium, and rhodium are used in catalytic converters, creating automotive emissions enriched in these elements. Modern road dust and sediments near highways show elevated platinum group elements from catalytic converter wear. An ancient civilization using similar catalytic technologies might create a global or regional enrichment in platinum group elements. The challenge is that asteroid impacts also enrich sediments in these elements. The Cretaceous Paleogene boundary layer contains elevated iridium and other platinum group elements from the Chicxulub impact. Distinguishing a technological enrichment from an impact requires examining the full geochemical context. Impact layers contain shocked quartz, spherules, and other diagnostic features. They also show characteristic platinum group element ratios matching chondritic meteorites. A technological enrichment would have different ratios reflecting industrial use patterns and wouldn't be associated with impact features. Lead isotopes offer particularly good potential for detecting ancient technology. Natural lead has 4 stable isotopes produced by radioactive decay of uranium and thorium. The ratios between these isotopes depend on the age and uranium-thorium content of the rocks from which lead was eroded. Different geological provinces have characteristic lead isotope signatures. Industrial lead, particularly from ore deposits, gets redistributed globally through human activities. Leaded gasoline added tetraethyl lead from specific ore sources to the atmosphere worldwide. Lead from smelting, batteries, and paint similarly spread ore-derived lead far from its source. This creates lead isotope anomalies in sediments, where lead with specific isotope ratios appears in locations inconsistent with local geology. An ancient civilization mining and smelting lead would create similar anomalies. We'd see lead with isotope ratios indicating specific source rocks appearing in sediments globally or regionally. The ratios wouldn't match local bedrock and couldn't be explained by natural weathering and transport. The problem is that lead is mobile during diagenesis. Groundwater can leach lead from sediments and redeposit it elsewhere, potentially erasing or overprinting original depositional isotope ratios. Only in sediments that remained chemically stable for millions of years would the original signature be preserved. Deep ocean sediments that were never buried deeply enough to alter their chemistry might retain such signatures. Mercury provides another potential marker. Industrial processes release mercury to the atmosphere through coal combustion, gold mining, and manufacturing. Mercury has 7 stable isotopes that undergo mass-dependent and mass-independent fractionation during various processes. Industrial mercury has isotope signatures distinct from natural background. An ancient civilization using mercury in technology or releasing it through industrial processes would create mercury isotope anomalies in sediments. The signature would need to be distinguished from natural mercury variations caused by volcanic activity and weathering. Multiple isotope systems showing correlated anomalies would strengthen the case for technological origin. Synthetic molecules represent the most unambiguous chemical signature if they could be found. Molecules that don't exist naturally and couldn't be produced by any known abiotic or biological process would prove technology. The challenge is that most synthetic molecules degrade over thousands to millions of years. Certain molecular structures are particularly unlikely to form naturally. Complex aromatic compounds with specific substitution patterns, molecules with unusual stereochemistry, polymers with regular repeating units, all suggest synthesis. Finding such molecules in ancient rocks would require them to survive geological time, which most wouldn't. Biomarker molecules do survive for hundreds of millions of years in some sedimentary rocks. These are relatively simple organic molecules derived from lipids in cell membranes and other biological structures. They're found in petroleum and ancient sediments, providing information about ancient life. If synthetic molecules with similar chemical stability were produced by an ancient civilization, some fraction might survive. The search strategy would involve analyzing organic compounds in ancient sediments, looking for molecular structures that don't match any known natural products. This requires sophisticated organic geochemistry, using gas chromatography, mass spectrometry, and other analytical techniques. Currently, such analyses focus on finding natural biomarkers, not synthetic molecules, so ancient synthetic compounds could be present but unrecognized. Physical signatures beyond chemistry and isotopes offer another category of evidence, though generally less likely to survive millions of years. Physical structures, even if destroyed, might leave traces in the form of stratigraphic anomalies, unusual sedimentary features, or geophysical signatures. Mines and quarries create specific geological signatures. Underground mines leave voids that might be detected through seismic surveys or gravity anomalies if they haven't collapsed. Open pit mines create topographic features and disturb stratigraphic sequences. Even if filled in over millions of years, the disturbance might be detectable through careful geological mapping. The problem is that natural processes also create voids and disturb stratigraphy. Caves form through dissolution of limestone. Volcanic pipes create vertical structures. Mass wasting disturbs layering. Distinguishing ancient mining from natural features requires finding characteristics unique to artificial excavation, like regular geometric patterns or evidence of tool marks on rock surfaces. Tool marks themselves are unlikely to survive. Erosion and weathering remove surface details rapidly on geological timescales. Even in protected environments, mineral recrystallization and rock alteration would erase fine-scale features. We wouldn't expect to find recognizable tool marks on rocks millions of years old. However, large-scale geometric patterns might survive if preserved in the stratigraphic record. An ancient quarry with rectangular excavations might leave a pattern visible in cross-section if later filled with sediment and lithified. The sediment fill would have different characteristics from surrounding undisturbed strata, potentially allowing recognition even after metamorphism. Artificial levees and earthworks might leave subtle traces. Modern humans have created massive earthworks for agriculture, flood control, and construction. These features reshape topography and create sedimentary patterns distinct from natural deposition. If buried and preserved, they'd create stratigraphic anomalies. An ancient civilization building similar structures might leave detectable patterns in sedimentary sequences. We'd look for layers showing evidence of artificial emplacement, unusual sorting, or geometric arrangements that don't match natural processes. This requires detailed stratigraphic analysis and would be easily confused with natural features unless the patterns were unambiguous. Concrete and ceramics might leave recognizable traces if their mineralogy differs from natural rocks. Portland cement concrete creates specific mineral assemblages when it cures. These assemblages might survive diagenesis in recognizable form, though they'd look similar to some naturally cemented sediments or metasomatized rocks. Distinguishing ancient concrete from natural rock requires identifying the specific mineral assemblages and cement structures characteristic of artificial concrete. This might be possible through detailed petrographic and geochemical analysis, but it would be challenging because diagenesis and metamorphism alter both natural and artificial materials. Ceramics fired at high temperatures create mineral assemblages that might survive. The problem is that natural processes also fire rocks. Contact metamorphism, when magma intrudes sediments, can bake rocks at temperatures similar to ceramic kilns. Distinguishing fired ceramics from contact metamorphism requires finding evidence of the original clay composition and firing conditions inconsistent with natural heating. Glass, as discussed earlier, might survive in altered form. Devitrified glass has a microcrystalline texture distinct from most natural rocks. Finding glass fragments in sediments from periods when volcanic activity was minimal in that region could suggest artificial glass, but proving artificial origin would be difficult without additional evidence. Metals in artifacts would corrode and disperse over millions of years. However, unusually concentrated metal deposits in unexpected geological contexts might indicate former artifacts. Finding copper enrichment in a sediment layer with no natural source for the copper associated with other technological signatures could be suggestive. The shape of corroded artifacts wouldn't survive, but the geochemical anomaly might. We'd need to find metal concentrations that are localized, inconsistent with natural ore deposits, and associated with other evidence of technology. Metal alone wouldn't be diagnostic because natural hydrothermal and sedimentary processes concentrate metals. Urban heat islands and atmospheric pollution create subtle signals that might be preserved. Cities are warmer than surrounding countryside due to waste heat and altered albedo. This warmth affects local climate and might influence pollen distributions or isotope ratios in sediments. Ancient cities might have created similar effects detectable as local climate anomalies in the geological record. Soot from industrial combustion deposits in sediments and ice. Modern industrialization has increased soot deposition globally, visible in ice cores and sediment records. An ancient industrial civilization would create similar soot deposition. The challenge is distinguishing industrial soot from natural sources like wildfires and volcanic activity. Soot from different sources has different characteristics. Elemental carbon from industrial combustion has different morphology and chemical signatures than charcoal from wildfires. The particle size distributions differ. The isotope ratios of carbon can distinguish between burning of fossil fuels versus biomass. Finding a sediment layer with soot characteristics matching industrial combustion, occurring globally or across a wide region, coinciding with other technological signatures, would strengthen the case for ancient civilization. But soot alone wouldn't be conclusive, because natural conflagrations can create similar deposits. Microplastics represent a uniquely modern signature currently being deposited in sediments worldwide. These small plastic particles are accumulating in oceans, lakes, and soils. They'll be incorporated into sedimentary rocks and might survive for millions of years in altered form. An ancient civilization using plastic materials might have created similar microplastic deposition. The particles would degrade over time, but might leave traces as unusual organic-rich particles or distinctive organic molecular fragments. Finding microplastic-like particles in ancient sediments would require showing they have characteristics inconsistent with natural organic matter. The combination of multiple signatures provides the strongest evidence. No single anomaly is conclusive because natural processes create enormous variability. But finding several independent signatures coinciding in time and potentially in space becomes increasingly difficult to explain naturally. For example, finding a sediment layer with carbon isotope anomaly, uranium isotope depletion, rare earth element pattern inconsistent with natural fractionation, and elevated platinum group elements not associated with impact features would be highly suspicious. Each signature individually might have a natural explanation, but the combination would be harder to explain. This is the forensic approach to searching for ancient civilizations. We're not expecting to find smoking guns like intact artifacts. We're looking for constellations of evidence that collectively point toward technology, despite each piece individually being ambiguous. The standard of proof must be high, because the claim is extraordinary. The search also requires knowing where to look. Sedimentary sequences that accumulated continuously over long time periods in stable depositional environments are ideal. Deep ocean sediments, large lake deposits, and certain continental margin sequences provide good candidates. These settings preserve environmental signals with minimal interruption and alteration. Specific time periods might be more promising to examine. Periods following mass extinctions, when ecological niches were empty and opportunities existed for rapid evolution, might be times when intelligence could have evolved. Examining sediments from immediately after the Permian-Triassic extinction or the Cretaceous-Paleogene extinction might be strategic. But this assumes ancient civilizations would arise soon after extinctions. They might have arisen during stable periods when ecosystems were well established. Without knowing when to look, we'd need to examine sediments spanning Earth's entire history, an enormous undertaking. The null hypothesis remains that no ancient industrial civilizations existed. This hypothesis is supported by the absence of detected signatures despite substantial geological research. While this research hasn't specifically targeted Silurian hypothesis signatures, any obvious anomalies would likely have been noticed and investigated. The alternative hypothesis, that ancient civilizations existed but left no detectable trace, or left traces we haven't yet recognized, is logically possible but unsupported by current evidence. Proving this hypothesis requires finding the signatures discussed in this chapter in geological contexts that exclude natural explanations. The search continues not because we expect to find ancient civilizations, but because the question is scientifically legitimate and the methodology has value. Developing techniques to detect technological signatures in Earth's geological record informs our search for biosignatures and technosignatures on other planets. If we know what to look for on Earth, we'll be better prepared to recognize similar signatures elsewhere. In the final chapter, we'll explore why this question matters beyond satisfying curiosity. The Silurian hypothesis connects to fundamental questions about the frequency of intelligent life in the universe, the longevity of technological civilizations, and the likelihood of detecting extraterrestrial intelligence. It also forces us to confront what traces our own civilization will leave, and whether future species on Earth or elsewhere might one day ask the same question about us. The question of whether ancient industrial civilizations could have existed on Earth without leaving detectable traces isn't just an academic exercise in geological detective work. It connects directly to the most profound question humanity has ever asked. Are we alone in the universe? The Silurian hypothesis forces us to reconsider what we think we know about the prevalence of intelligent life, the durability of technological civilizations, and our chances of ever detecting alien intelligence. If we can't even be certain we're the first technological species on our own planet, what does that tell us about the cosmos? The implications are staggering, and they fundamentally reshape how we should think about our place in the universe and our search for others like us. The Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" captures a troubling contradiction at the heart of astrobiology. The universe is vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Many of these stars have planets, and many of those planets exist in habitable zones where liquid water could exist. The ingredients for life, organic molecules and energy sources, appear to be common throughout the cosmos. Given these numbers and the apparent ubiquity of life's building blocks, intelligent civilizations should be common. Yet we see no evidence of them. We detect no alien radio signals despite decades of searching. We see no obvious signs of astroengineering projects like Dyson spheres. We find no evidence of interstellar colonization or galactic-scale civilizations. The universe appears silent and empty of intelligence beyond Earth. This silence is the Fermi paradox, the jarring disconnect between the expectation of abundant alien civilizations and the observation of none. Dozens of potential solutions have been proposed to resolve this paradox. Perhaps intelligent life is extraordinarily rare, requiring such unlikely evolutionary circumstances that it happens only once or twice per galaxy. Perhaps technological civilizations destroy themselves shortly after developing advanced technology, leaving no time for interstellar expansion. Perhaps aliens exist but deliberately avoid contact. Perhaps the galaxy is colonized, but Earth is being preserved as a nature reserve. Perhaps we're looking in the wrong ways or at the wrong times. The Silurian hypothesis adds a disturbing new dimension to this puzzle. It suggests that technological civilizations might be more common than we think, but they leave such minimal traces that we wouldn't recognize them even if they existed in our own planet's past. If this is true on Earth, it might be true throughout the galaxy. Technological civilizations could rise and fall repeatedly, separated by millions of years, never overlapping in time, each one unaware of its predecessors and successors. This possibility fundamentally changes the Fermi paradox calculation. Instead of asking, "Where is everybody right now?" we should ask, "Where has everybody been throughout cosmic history?" The answer might be that civilizations exist or have existed on many worlds, but they're so temporally and spatially isolated that contact is impossible. We're not alone in the universe, we're just alone in time. Consider the timescales involved. Earth has existed for 4.5 billion years. Complex multicellular life has existed for about 600 million years. Humans have had industrial technology for roughly 250 years. If our industrial civilization lasts another 10,000 years before collapsing or transcending to something unrecognizable, we'll have been detectable as a technological civilization for perhaps 20,000 years total. 20,000 years is 4/100,000ths of 1% of Earth's history. It's a geological eye blink, so brief that it barely registers. If technological civilizations on other planets have similarly short durations, the galaxy could contain thousands or millions of dead civilizations whose brief moments of detectability never overlapped with ours. The Drake equation, used to estimate the number of detectable civilizations in the galaxy, includes a term for the average lifetime of technological civilizations. This term, usually represented as L, is perhaps the most uncertain parameter in the equation. Optimistic estimates suggest civilizations might survive for millions of years, becoming galactic empires that endure across cosmic timescales. Pessimistic estimates suggest most civilizations destroy themselves within centuries of developing nuclear weapons or advanced industrial technology. If the Silurian hypothesis is correct and technological signatures fade within millions of years, then L should be interpreted differently. It's not just the lifetime of the civilization, but the lifetime of detectable traces. Even if a civilization survives for millions of years, if it leaves no permanent mark on its planet or surroundings, it effectively has a short L from the perspective of future observers. This creates multiple ways to be invisible in the galaxy. A civilization could be invisible because it existed in the past and its traces have faded. It could be invisible because it exists in the present but far from us and isn't broadcasting detectable signals. It could be invisible because it has transcended physical form or retreated into virtual realities, no longer manipulating matter at scales we can observe. Or it could be invisible because we're looking for the wrong signatures. The longevity question is central to understanding the Fermi paradox. If technological civilizations typically survive for millions of years, becoming stable galactic citizens, then we should expect to see them everywhere. The galaxy is over 13 billion years old. Even if civilizations arise rarely, millions of years of existence per civilization would create overlap. Some should be visible to us now. But if civilizations typically last only thousands or tens of thousands of years before collapsing or transforming beyond recognition, then the galaxy could produce thousands of civilizations that never overlap temporally. Each would be alone in time, separated from others by millions of years. The total number of civilizations that have existed could be large, while the number existing at any given moment remains small, possibly one. Our own civilization's trajectory offers little comfort about longevity. We face multiple existential risks: nuclear war, climate change, pandemic disease, artificial intelligence alignment problems, biotechnology disasters. We've had nuclear weapons for less than 80 years and have come frighteningly close to using them multiple times. We've been altering climate for less than 2 centuries and are already seeing destabilizing effects. We're developing artificial intelligence and biotechnology with transformative and potentially catastrophic potential. Will we survive another century, another millennium? It's genuinely uncertain. And if humans, with all our advantages of being aware of existential risks and actively trying to mitigate them, struggle to ensure long-term survival, what does that suggest about the typical fate of technological civilizations? Perhaps self-destruction shortly after reaching technological capability is the norm rather than the exception. This possibility is sometimes called the Great Filter, a concept that suggests there's some extremely difficult step in the evolution from simple matter to galaxy-spanning civilizations. The filter eliminates most potential civilizations before they reach detectability. The question is where this filter lies. Is it behind us, perhaps in the origin of life, or the evolution of intelligence? Or is it ahead of us, lurking in the challenges faced by young technological civilizations? If the filter is behind us, then life is extraordinarily rare, but civilizations that do arise have good chances of long-term survival. If the filter is ahead, then life might be common, but technological civilizations almost always destroy themselves or hit developmental dead ends. The Silurian hypothesis is relevant because it suggests ways the filter could be ahead of us, while still being consistent with the apparent absence of ancient civilizations on Earth. If most civilizations last only thousands of years and leave minimal geological traces, Earth could have hosted previous technological species without us knowing. The filter would be ahead of us because those civilizations didn't survive, but their failure wouldn't be obvious from the geological record. This is simultaneously reassuring because it means Earth can produce technological intelligence multiple times, and terrifying because it means all previous attempts apparently failed to achieve long-term stability. The temporal isolation created by brief civilization durations also affects the probability of contact. Even if civilizations exist on many planets, if they exist for only brief periods separated by millions of years, the chance of two civilizations existing simultaneously and within communication range is tiny. The galaxy could be full of life without any two civilizations ever making contact. This has implications for SETI, the search for extraterrestrial intelligence. SETI programs scan the sky for radio signals or other electromagnetic signatures of technological civilizations. The assumption is that civilizations broadcast signals intentionally or as leakage from communications and other activities that we can detect across interstellar distances. But if civilizations exist only briefly, the time window for detecting their signals is correspondingly brief. Radio waves travel at light speed, so signals from a civilization 1,000 light years away take 1,000 years to reach us. If that civilization existed for only 10,000 years before collapsing, we have a 10,000-year window to detect them, and only if we happen to be looking at the right star system during that window. The probability of successful detection becomes a matter of timing. With billions of star systems in the galaxy and civilizations existing for only brief periods, the chance of our detection window overlapping with their broadcast window for any particular star is minuscule. We'd need to search millions of stars for decades to have reasonable probability of detecting even one civilization if they're short-lived. This pessimistic assessment doesn't mean SETI is worthless. Even small probabilities are worth investigating when the discovery would be so profound. And SETI can detect very long-lived civilizations if any exist. If even one civilization in the galaxy survives for millions of years and broadcasts continuously, SETI might find them. The null results so far tell us that such civilizations aren't common, but they don't rule out existence of brief civilizations we haven't detected yet. The Silurian hypothesis also affects how we interpret biosignatures on exoplanets. Next-generation telescopes will be able to analyze the atmospheric composition of planets around other stars, searching for signs of life. Oxygen, methane, and other gases in combinations that suggest biological production would indicate life exists or existed on those worlds. But what about technosignatures? Could we detect evidence of industrial civilizations on exoplanets? If such civilizations exist briefly and leave minimal traces, detecting them would require observing planets at exactly the right time during their industrial period. The probability of this is very low unless industrial civilizations are common and long-lived. We might detect dead civilizations through geological signatures if those signatures persist and are observable remotely. But most of the signatures discussed in previous chapters, isotopic anomalies and chemical patterns, wouldn't be detectable from interstellar distances. We can't analyze the detailed geochemistry of exoplanet rocks from light years away. We can only observe atmospheric composition and gross spectral features. This means remote detection of past civilizations is nearly impossible. We might observe a planet with an oxygen-rich atmosphere indicating photosynthetic life existed at some point. But we wouldn't know if that life had evolved intelligence and technology millions of years ago. The industrial signatures would be invisible to our telescopes. only civilizations currently active during our observation would be detectable through atmospheric pollution or other obvious signals. Industrial pollutants in an exoplanet's atmosphere, artificial illumination on the night side, or large-scale engineering projects might be observable, but all of these require the civilization to exist at the exact time we're observing, a timing coincidence that's unlikely if civilizations are brief. The implications for the rare Earth hypothesis, which suggests that Earth-like planets and complex life are extremely uncommon, become more nuanced. Perhaps Earth-like planets are common and complex life is common, but technological civilizations are brief and leave minimal traces. The galaxy could be full of life-bearing planets that occasionally produce technological intelligence, but the probability of detecting that intelligence remotely is negligible because the technological phases are so short. This would resolve the Fermi paradox by suggesting that intelligence is neither extremely rare nor extremely common, but rather that it's episodic and brief. Many planets might evolve intelligence given enough time, but each instance exists for such a short period that overlap between civilizations is rare. We're not seeing aliens because they're not out there right now, even though they've existed in the past and will exist in the future. The question of what happens to civilizations after their industrial phase becomes crucial. Do they destroy themselves completely, leaving a lifeless planet? Do they collapse back to pre-industrial states, with survivor populations continuing at lower technology levels? Do they transcend to post-biological existence, uploading minds to computers or transforming into forms we wouldn't recognize as civilization? Do they deliberately limit their technology to sustainable levels? Each outcome has different implications for detectability and for the longevity question. Total self-destruction would leave minimal traces and suggest the Great Filter is ahead of most civilizations. Collapse to pre-industrial states might allow recovery and multiple cycles of technological development on the same planet. Transcendence to post-biological existence might make civilizations invisible to our search methods while allowing them to persist indefinitely. Deliberate limitation might allow long-term survival, but at technological levels below detectability. We don't know which outcome is most likely, because we have only one example, ourselves, and we haven't reached any of these outcomes yet. This uncertainty makes predicting the fate of civilizations and their signatures extremely difficult. The Silurian hypothesis acknowledges this uncertainty by asking what would be visible if various outcomes occurred millions of years ago on Earth. The hypothesis also connects to the zoo hypothesis, the idea that aliens exist, but deliberately avoid contact with us. If many civilizations have existed throughout the galaxy's history, perhaps some survived long enough to spread and establish galactic norms. These elder civilizations might enforce a non-interference policy, allowing younger civilizations to develop without contact. But if civilizations are typically brief and leave minimal traces, the zoo hypothesis becomes less plausible. There might not be any elder civilizations currently existing to enforce non-interference. The galaxy might be full of young civilizations that arise, exist briefly, and disappear without ever meeting each other. We're not in a zoo. We're in a vast, empty house where other occupants occasionally exist, but in different rooms at different times. The timing question becomes even more poignant when we consider that our industrial civilization is creating existential risks that might lead to our own brief existence. Climate change, nuclear weapons, engineered pandemics, and unfriendly artificial intelligence all pose threats that could end technological civilization or dramatically reduce human population within the next few centuries. If we don't survive these challenges, what traces will we leave? As discussed in previous chapters, most of our surface infrastructure will be gone within thousands of years. Within millions of years, only subtle geochemical signatures might remain. Future intelligent species evolving on Earth millions of years from now might face the same uncertainty about us that we face about potential predecessors. This creates a humbling perspective. We might be just one in a series of civilizations on Earth, each arising, achieving technology, and failing to achieve stability. The planet might repeatedly experiment with intelligence, giving different species their chance at technological development. None so far has succeeded in creating enduring civilization, at least not in ways that left obvious traces. Or perhaps we're the first, and the pattern of brief civilization duration is universal, not just on Earth but throughout the galaxy. Perhaps the laws of physics, the nature of energy resources, or the structure of intelligence itself makes long-term technological civilization extraordinarily difficult to maintain. The challenges we face, resource depletion, environmental degradation, weapons of mass destruction, might be universal challenges that all technological species encounter and most fail to overcome. The anthropic principle adds another layer to this reasoning. We can only observe the universe from a time and place where observers exist. If civilizations are brief, we necessarily find ourselves existing during a civilization's brief technological phase, because that's the only time when observers capable of asking these questions exist. We can't observe the long periods between civilizations because no observers exist then. This means our observation that we exist during a civilization's technological phase tells us nothing about how common such phases are. We're guaranteed to find ourselves during one because otherwise we wouldn't exist to observe. This is called observation selection bias, and it makes reasoning about civilization frequency from our single example extremely difficult. The doomsday argument, a controversial application of anthropic reasoning, suggests that we're more likely to be living during the middle period of humanity's total duration rather than very early or very late. If this argument is correct and humanity's total duration is short, we should expect to be relatively close to the end. This is deeply unsettling because it suggests brief civilization duration might be the norm. However, the doomsday argument is disputed and might not apply correctly to questions about civilization duration. The anthropic reasoning is tricky and potentially misleading. We should be cautious about drawing strong conclusions from such arguments. Nevertheless, they highlight the difficulty of reasoning about civilization longevity from our single example. The Silurian hypothesis also affects how we think about planetary protection and avoiding contamination of other worlds. If we might be able to detect ancient civilizations through subtle signatures in planetary geology, we need to be careful not to contaminate other worlds with Earth materials that might create false signatures of technology. Mars exploration already follows planetary protection protocols to avoid contaminating Mars with Earth life. But if we're serious about searching for technosignatures in Martian geology, we need to be even more careful. Human contamination could introduce isotopic anomalies, synthetic molecules, or other signatures that might be mistaken for ancient Martian civilization. This becomes particularly important if we establish permanent human presence on Mars. Our activities will create geochemical signatures that will be preserved in Martian sediments. Future geologists studying Mars millions of years from now will find these signatures and need to distinguish them from any hypothetical ancient Martian civilization. We should document what we're doing thoroughly to help those future investigators. The same considerations apply to moons like Europa and Enceladus that might harbor life in subsurface oceans. If we, contaminate these environments with Earth materials, we might make it impossible to determine whether any biosignatures or technosignatures we find are indigenous or introduced. The Silurian hypothesis reminds us that technological signatures can persist for millions of years and might be very difficult to distinguish from natural features without careful analysis. The philosophical implications of the Silurian hypothesis extend beyond astrobiology to questions about knowledge, certainty, and the limits of scientific inquiry. It demonstrates that there are questions about the past that might be fundamentally unanswerable given the available evidence. We might never know with certainty whether ancient industrial civilizations existed on Earth because the evidence has been destroyed by geological processes. This uncertainty is uncomfortable for science, which seeks definitive answers based on evidence, but it's an honest acknowledgement of the limits of what we can know about deep time. The geological record is incomplete, and some information has been permanently lost. We can make inferences and assign probabilities, but we can't achieve certainty about events millions of years ago that left minimal traces. This has parallels to uncertainty in cosmology about the universe's state before the cosmic microwave background, or uncertainty in quantum mechanics about the state of systems before measurement. Some questions might be unanswerable not because we lack sufficient technology or intelligence, but because the information needed to answer them no longer exists or never existed in accessible form. The practical response to this uncertainty is to continue gathering evidence while acknowledging the limits of what that evidence can tell us. We should search for technological signatures in the geological record, not because we expect to find them with high probability, but because the question is important, and the search might reveal unexpected insights about Earth's history and the preservation of information over geological time. The search for ancient civilizations on Earth also serves as practice for searching for evidence of life and intelligence on other planets. The techniques we develop to detect subtle technosignatures in Earth's geological record will be applicable to analyzing samples from Mars, Europa, or exoplanets if we ever obtain them. Learning what signatures survive and how to recognize them despite geological alteration prepares us for similar investigations elsewhere. Moreover, the negative results of finding no convincing evidence of ancient civilizations on Earth, assuming the search continues and remains negative, would itself be informative. It would suggest that either technological intelligence is very rare, arising only once in Earth's history, or that technological civilizations are so brief and leave such minimal traces that even on their home planet, they become undetectable within millions of years. Either conclusion has implications for SETI and for estimating the prevalence of intelligence in the universe. If intelligence is very rare on Earth, despite hundreds of millions of years of complex life, it's probably very rare on other planets too. If intelligence can arise but leaves minimal traces, then the galaxy might be full of extinct civilizations we'll never detect. The Silurian hypothesis ultimately forces us to confront our cosmic significance and temporal fragility. We might be one of many intelligent species to inhabit this planet, special not in being the first or only, but simply in existing now. Our achievements, which seem so important to us, might be forgotten completely within a few million years, leaving only the faintest chemical whispers in rock layers that future geologists might never examine. This perspective is simultaneously humbling and motivating. Humbling because it reveals how temporary our existence might be, and how little we might ultimately matter in the grand sweep of geological time. Motivating because it highlights the urgency of addressing existential risks and working toward long-term civilizational stability. If we want to be remembered, if we want our existence to matter beyond the brief present, we need to survive and thrive for millions of years, embedding our presence in the solar system deeply enough that it cannot be erased. The alternative is to accept brief existence as perhaps inevitable or even acceptable. Perhaps civilizations are meant to be ephemeral, burning brightly for a few thousand years before fading. Perhaps the galaxy is a vast dark forest where brief candles of intelligence flicker into existence and then go out, too distant in space and time to ever illuminate each other. Perhaps we're alone not because intelligence is rare, but because it's never synchronous. This existential loneliness is perhaps the deepest implication of the Silurian hypothesis. Even if we're not the only intelligence the universe has produced, we might be the only one existing right now, separated from our predecessors by millions of years of extinct silence and from our successors by millions of years of not yet existence. We could be surrounded by ghosts, the faint traces of dead civilizations, and by the potential for future intelligence that hasn't yet emerged. The question, could we detect an ancient industrial civilization, becomes, does our existence matter if we're destined to become equally undetectable ghosts in the deep future? The answer depends on what we do now. If we collapse within centuries, we'll leave minimal traces and become another potential undetectable civilization for future intelligence to wonder about. If we survive and spread beyond Earth, we'll embed our existence in the solar system in ways that can't be easily erased, colonizing other worlds, establishing self-sustaining populations throughout the solar system, perhaps eventually reaching other star systems. These would create redundancy that prevents total erasure. Even if Earth's geological record is eventually completely recycled, evidence of our existence would remain on the Moon, on Mars, in the asteroid belt, places where geological activity is minimal and surfaces preserve information for billions of years. The ruins of our lunar bases or Martian settlements could survive billions of years, clear evidence that technological civilization once existed in this solar system. Future intelligence, whether evolved on Earth or arriving from elsewhere, would find these ruins and know they weren't alone in time. We would have left a message that transcends geological erasure, a message written in architecture and artifacts rather than in rock chemistry. This long-term perspective transforms how we think about space exploration. It's not just about scientific discovery or resource utilization. It's about ensuring our existence leaves a mark that cannot be erased, establishing our presence in the cosmos in ways that will remain detectable for billions of years. It's about refusing to become ghosts, instead becoming ancestors that future intelligence can recognize and perhaps learn from. The Silurian hypothesis is ultimately about two kinds of time: the deep time of geology that erases nearly everything, and the potentially vast future time that we might inhabit if we survive our current challenges. It asks us to think beyond our immediate concerns to the million-year and billion-year timescales on which planetary and cosmic evolution operates. It challenges us to consider whether we want to be a brief anomaly in Earth's history or the beginning of something that endures. The answer to whether we could detect ancient industrial civilizations on Earth is probably no. If they existed more than a few million years ago and never left Earth's surface, the geological record is too incomplete, the erasure too thorough, the signatures too ambiguous. But this uncertainty doesn't mean we're alone in time. It means that if others came before us and failed to achieve permanence, they vanished into the very rock they once walked upon, leaving us to face the same challenges they faced with no guidance from their experience. We might be the first. We might be the latest in a long series. We cannot know with certainty, but we can choose what kind of ancestor we want to be for whatever intelligence follows us, whether it's our descendants spreading through the galaxy or a new species that evolves on Earth millions of years after we're gone. We can choose to leave traces that survive geological erasure by spreading beyond Earth. Or we can risk becoming another undetectable ghost, a civilization that once was but left nothing behind, except questions future scientists might ask, but never answer. The Silurian hypothesis shows us the stakes. Deep time is coming for all of us, and it will erase almost everything we build and do. The question is whether we let it erase us completely, or whether we establish ourselves across the solar system and beyond, creating permanence through distribution and redundancy. The choice is ours, and the clock is ticking. Not on human timescales of years or decades, but on geological timescales of millions of years, which sounds like plenty of time until you remember that millions of years pass in cosmic eye blinks, and civilizations that don't achieve stability might have only thousands of years, not millions. We don't know if ancient industrial civilizations existed on Earth before us. We probably never will know with certainty. But we can decide whether future civilizations will face the same uncertainty about us. That decision, more than any archaeological discovery or geological analysis, might be the most important implication of the Silurian hypothesis. It's not about the past, it's about the future, and whether we'll exist in it long enough to matter.